This is a recording on the overhead incurred by different types of catching the IF flag. So the IF flag, stands for interrupt flag, but as we saw in class, it doesn't have to be interrupts. You could do polling to do it. So basically, what I want to do here is to run different scenarios for the way that we catch T1 IF or T2 IF and see how much overhead we have, how much latency we have, how many cycles we're going to lag behind in responding to that particular event. And also there's going to be a distinction between events that are repetitive, like you want to blink RB2 every 100 milliseconds and repeat that forever, as opposed to something that you want to do just once. There's something in the calculation that is going to change, and also in terms of the latency and the kind of accuracy that you would get, these would basically differ. So the way that I'm setting things up is doing both polling and interrupts. So the goal here is to uh, flip RB2 every 100 milliseconds. Okay, so RB2 is going to basically flip every 100 milliseconds. And what I'll do is I'll set up T1 to give me 100 times 1 millisecond delay. And I'll do polling and interrupt. And also I'll do T2, which I set it up as 100 milliseconds, and it happens only once. And I'm going to do it both in terms of polling and also in terms of interrupts. Now, for the polling, I'm going to have two cases. And I'll explain, what I mean by these two cases. But there is one case in which I reset timer TMR1 equal to 0 in the loop, and in another case I will not set timer 1 to 0 inside the loop. Okay, and what I want to know is the number of instruction cycles and time in milliseconds that it takes to do this stuff. Okay, so basically simple a program that I need to do. Why did I do T1, T2? Because they're pretty much similar in terms of the pre-skaters and in terms of the way that they work. I just wanted to make the separation so that it's clear to, I could have done the whole thing with T1, configuring it differently every time, but this gives a more clear picture of what we're going to do. And basically the question is any of these methods better compared to the other? Is any one of them is going to give me better accuracy or not? Okay, so let's go to the program, and this is a code that I've written, and essentially in the case that you want to implement T1 as an interrupt, so this is the code for T1 interrupt. Okay, now I just reset timer 1 IF, I increment a variable msec, milliseconds, and just like any loop that you want to write. So if you remember in class, we wrote a loop in the polling version, and then when we wanted to convert it to interrupts, basically what we did was we did a count inside the interrupt routine. There is no while loop inside the interrupt routine, and I check to see if I have reached my limit, which is 100. I want to wait for 100 milliseconds to do things. So if 100 milliseconds has not reached, if I haven't reached that, and let's say I've only passed 23 milliseconds, so basically I just increment it to 24, and because it hasn't reached, I just get out of here, right? I just get out of the interrupt. But when I reach that 100, I reset this back to 0 because I want to do this in a cycle. I want to do this repeatedly, and I'll do whatever that I want to do. So let's say I want to flip RB2, then I'll just XOR RB2 with 1, which is essentially flipping it. Okay, so this is our T1, which is doing every 1 milliseconds, and then I need to do 100 iterations of it. Now T2's in an interrupt version, all I need to do is you have to ask the question, when am I going to be brought here? And if you set up the prescaler and the PR2 correctly to give you 100 millisecond the delay between it gives you the IF flag, then I'm here because 100 milliseconds has passed, so there is no loop here. As soon as you're here, you just have to reset your T2IF and flip your RB2. There's a funny story here that why I have this statement. By the way, if you want to write assembly inside your C program, you can basically do this. You would just say ASM, and in parentheses and quotations, you would just write your assembly instructions. Of course, I mean, the assembly instructions that you put in here are going to be a little bit different, and you have to be very careful how you're going to use your variables. We will play with data stuff, some nasty stuff if you want to access the variables, the parameters of the function, and so on. But when you're dealing with things like port B, then basically you just use BTG port D and then the #2. Now the reason I put this is because I looked at the disassembly listing and I was amazed how many instructions the compiler is going to use just to flip this RB2. I'm going to show you later. I mean 7 or 8 instructions. But for now, let's just move on. And in our setup, I just set up RB2 as output here, setting up T2 to generate T2IF every 100 milliseconds. Let me do this. I'm sure everybody knows this by now, but let me just repeat that just to make sure that everyone understands. So for T2, the calculation that I want to have is I want it to give me a delay of 100 milliseconds, right? Which is 0.1 second. And this delay is going to be the frequency, which is 1/16 megahertz, times PR2, and sometimes we use this +1. I'll talk about it. In this particular case, we don't need that. Times my prescalers. Okay? And if you solve for this, if I call this n, right, then you're going to see that if I multiply these two sides, essentially I'm going to get 1.6 million equals n, which obviously is greater than 65536, which is 65535, in fact, which is the largest that a 16-bit register is going to pick, is going to hold. So obviously I can't do this with prescaler of 1. Let's go ahead and use a prescaler of, let's say, 256. Then for n, you're going to, so if I set prescaler is 256, then your n is going to be 1.6 million divided by 256, and that's going to be a number, whatever it is. You put that in PR2. Sorry, this is not n. N is the multiplication of these two. So if I choose prescaler to be 256, then PR2 would be the solution of this equation, and then you just set PR2 equal to that. Let's see what I did here. I chose a prescaler of 256, and a solution to my equation was 6250. And I'll tell you why I don't need that +1 thing here. But let me just show you that basically I reset T2IF and I turn on my timer 2. So from this point, when I turn on my timer 2, it's going to start counting TMR to equal whatever value it was. Note that here I haven't, oh yeah, I have reset it. So timer 2, TMR2 is going to increment to 1, 2, 3, 4, every 256 instruction cycles. Okay, and then later on, if I want to mark the beginning of 0 0.1 seconds, then I need to reset this again, because before I get to that, whatever point that I want to mark 0.1 second at that point, um, I might have done an overflow a couple of times, right? So you want to reset T2IF, and also you want to set TMR2 to 0, and that would begin a new cycle for 0.1 seconds. Now let me get back to this point of why I don't need to write this as 6249. Now, if I want to do, let's say, 1 millisecond repeatedly, all right? Let's say I want to do 100 times of 1 millisecond. So what I'll do is I will say, you know, something like for I equals 0 to or 1 to 100, okay, then wait for T1IF, reset T1IF, and then go back. All right. Now, what does this entail? Basically, what I'll do is my TMR1 to get me the 1 millisecond is going to count from 0, 1, 2, up to 15,999, and then go back to 0, 1, 2, 3, right? So the first iteration when I is equal to 1, let's say this goes from 1 to 100, I equal to 1, I count from 0 to 1599, and then I go to 1, 2, 3 up to 15,999, right? So you see, whatever value that I put in PR1, I counted from 0, 1, 2 up to that point. So up to this point, so when I start from 0 and 1 TCY gets me here, second TCY gets me here, 15,999 TCY will get me here. So up to this point, if I finish it here, if I say as soon as my T1IF has become 0, stop it, then I've counted 15,999. But when I go to 0, right, then I'm going to also count an additional one. So I'm going to count 16,000 for the whole duration of PR1. So when I'm doing a repeat and I go from 15,999 to 0 and then to 1 and then to 2, 3, if this is a loop and if I'm doing this continuously, then I have to add this plus 1. So in that equation then for TMR1, it becomes 1 over 16 mega times PR1 plus 1 times the prescalar for timer 1, right? Because I want to repeat this 1 millisecond thing. But when I'm doing my PR timer 2, which doesn't repeat, it starts with timer 2 at 0 and it counts to 1, 2, 3, 4, 5, 15,999, and then it stops. But then if I stop at 15,999, then I haven't counted 16,000. I need to do an additional one. So I'm going to initialize my PR2 to 16,000 to get the exact count that I want, including this, transition from 15,999 to 16,000, and that would give me an accurate number. Now for T1, for timer 1, I wanted it to give me 1 millisecond, so this is the code that you've seen a couple of times by now. We initialize it to 15,999 and we have our timer 1 set up. Now my main loop, I'm going to wait for these two timers to give me 100 milliseconds using polling first, and then I'll do interrupt after that. So if I want to do polling on T2, and remember T2 is set up to give me in one shot, give me 100 milliseconds for T2 IF. So I first turn it off because I want to mark the beginning of the 100 millisecond right here, right before I do the loop, right? And I reset TMR2 because who knows during the setup and whatever I do before here. I mean, here I'm not doing anything, but assume that your coworkers add some stuff here. Then who knows, you might have, done a couple of rollovers of T2, and now you want to reset it and start from a clean slate. So you reset TMR2, you reset T2IF, turn it on. Right? So from if I want to see if my polling method comes out of this while loop at exactly 100 milliseconds, what I need to do is to put a breakpoint here, and what happens? Put a breakpoint here and put a breakpoint here. So I need to start my stopwatch timer here and stop here, right? So this is going to tell me how long it takes, and then I'll do my RB2 RB2 flipped. Let me start the stopwatch too. If I can dock it here. If I can't, it's fine too. Alright, now if I need to do the same thing to give me 100 milliseconds on timer 1, then during the time that timer 2 was running, timer 1 has done an overflow multiple times. And note that here I haven't enabled the interrupts yet, so my code would not go to these interrupt service routines. Okay. Alright, but timer 1 was running in parallel with timer 2, so I do need to reset it and reset its T1IF, T on. And again, if I want to measure how long it takes, basically I have to put a breakpoint here, and then I have a loop that goes from 0 less than 100, and I'll just do while T1IF double equals 0, do nothing, reset T1IF, be ready for the next iteration of this count, and then after I do 100 counts of 1 millisecond, then I can go ahead and do the RB2 RB2 flipped. Now, some of you when writing this code might choose to also reset TMR1 to 0 to give it a clean slate and go the whole 0 to 15999 counts. I'm going to show you later why this is a bad idea. And let me show you what happens with the interrupt version. So for the interrupt version, what I'll do is I'll reset my timer to counter, I reset my IF, and I enable my interrupt routine, right? So if I want to know how long it takes from the time that I enable the interrupt, by the way, I don't have to turn off my timer, but what I'll do is I'll just set TMR2 right before I enable the interrupt. So when I do T2IE equal 1, TMR2 would be at 1, and it will, start counting. Now, I'm not going to enable my timer 1 yet, because the way that a stopwatch works is from a breakpoint that it stops, it runs until it hits the next breakpoint, and it will tell you how many cycles you had between these two breakpoints that you stop. So it doesn't have any cumulative way of telling me how many clock cycles I've had since the beginning of the program. If you guys find a way of doing it, let me know. I don't know how to do it. But I don't want the interrupt routines of timer 1 and timer 2 to interfere with each other and stop the stopwatch timer and every time tell me 1 millisecond has passed, another 1 millisecond has passed. I want this whole thing to give for the program, for the simulator, not to stop until I have the 100 milliseconds. So I'm going to test these two interrupt parts separately. I'm going to do each one take turns. All right, so let's go ahead and run the program, and then we'll see how many cycles we get, and see how long it takes to do these operations. And it would be a good idea for you to have a piece of paper, paper and pen, so that you can write down how many cycles you had. All right, let me just clear it. All right, so I'm at this point. I'm about to turn on timer 2, and timer 1 has counted 9 since setup happened, and I just set timer 2 to 0. And remember, timer 2 has a prescaler of 256, so it's going to count every 256 instructions that I run here. But let me go ahead and run it. It's taking a while here to mark 100 milliseconds. This is all one count of my timer 2. And note, this while loop gave me 16 million and 9, right? I have, no, 1.6 million and an extra 9 here. Okay, so pulling on T2 gives me polling on T2 gives me 1.6 million and 9, which is equivalent to 100.000562. 0.00562 milliseconds. All right, and your TMR2 is 6250, which is the value that you expected, and this hasn't incremented because your prescaler is 256. It takes a while for this to increment, but this is telling you that you had an extra 9 instruction cycles to catch this. And you have seen this in a previous video, right? I mean, if you look at the disassembly listing of this while loop, the while loop is going to take maybe an extra cycle to catch that IF, because the IF happened right after you fetched the value of I don't remember what register has it, T2 sorry, yeah, I don't remember, intcon something that has this T2IF flag in it. So it took a while for the while loop to check the value, so you have that extra 9 instruction cycles that you lost after doing that, right? Okay, so we can let it run up to this point. So this is the point that we reset our TMR1's counter, and now we are going to count for 100 times 1 millisecond instructions. And what I need to do is to set a breakpoint here, because I want to know how long it takes from the time that I turn on my timer and the time that I reach here. So let me go ahead and execute it. And we are going to execute this in more detail, but whoa, it took 1.6 million, but with a lot more overhead, right? So it is 1, and this is timer 1's with resetting TMR1 to 0. So it is here 1.601409, which is going to result in 100.088. I don't think I need to write the rest of it, but just to be complete, right? And you can see that this is way more than what you got in T2 polling. So it seems that doing 100 times of a 1 millisecond is not going to give you accurate results. It seems that there is a lot of overhead in the loop that you have to give you this. But as a matter of fact, this line is, oops, what happened? I think I have my insert. No. Alright, so this line is a bad line, and let's go ahead and rerun the program. And just to save time, because I've already tested this line, let me comment out this while loop so that we don't have to wait for T2 to give us the delay. Okay, so we are running it, and what happened? Maybe there's an error. Oh, I have a syntax error somewhere. Hopefully I haven't deleted anything important. Okay, so yeah, let's skip this breakpoint. This is the breakpoint for T2. All right, now I want to see how long this time it takes without that TMR equals 0. And I let it run for a while, and it gives me, and it stops here. And now look what I got. This is 15,999,989, which is 99.999312, without that TMR1 equals 0. Although it beats me why it's giving us a smaller value. Yeah, I guess I know. Yeah, that's probably the line that I deleted, and probably when I did delete, you guys were screaming, "No, don't delete that one." So I apparently forgot to do this before turning on timer. So sorry, busted experiment. Let's go ahead and run it again. Alright, skip the timer 2. Alright, here is what we want to test. So timer 1. Alright, now it gives me much better than that, the case in which I had TMR1 equals 0. So this time I have 1.6 million plus 14 extra. Okay, which is much closer to this 0.909 that I got here. And who knows, maybe I run it another time with a little bit more instructions before that T on and the loop, and sometimes this could even go down to 7 or so. So it's just a matter of how many instructions you take and when that T1 IF happens with respect to your loop body. So if it's right exactly right before when you fetch the register that has T1 IF, maybe you're lucky and this overhead gets down to 7 or so. So and let me note down the time. It's 100,000,875. 100.0000875, which again is close to this value that I had here and far from the really terrible solution that I had here. But the question is, why is there a difference between these two cases? So what I want you to do is to pause the video, think about why this is the case, and it might be a good idea for you to basically write down the way that I did in class multiple times. Write down the instructions that are running, and next to it show the timer 1 value, and don't shy away from going from iteration 1 to iteration 2 of the loop and trying to figure out what's going on, and then come back and see what my interpretation of it is. So you can pause the video now. Alright, now that you're back, let me show you what happens. So basically you have a for loop, right? So this is the iteration in which your count is 0, and then you have another iteration in which your count is 1, and then you have another iteration in which your count is 2. Okay? So what happens here, and it might be a good idea to maybe stop the program and execute the program up to this point and show you what happens at the assembly level. So let's go ahead and look at the window debugging disassembly, and let's look at the stuff here. All right. So this is before I enter the loop. Okay. And now when I go to the loop body is going to do a bunch of stuff for the count and checking to see if count has reached 100, which is hex 63. And then I have this big while loop that I'm going to be spending most of my time waiting for the 1 millisecond to happen, and then clear IFS 0 and move on, right? So let's go ahead and take a look at this, the end of the while loop. So the end of the while loop is supposed to be exactly when my TMR1 value is that 15999, right? So if I go ahead and execute it up to this point, my TMR1 has incremented to 4, right? So this while loop that wanted to catch the TMR1 value right when it's 0, it had a lag of 4 catching it. And the next time that I execute it's going to be 6. The next time it's going to be 3. Next time it's going to be 5. 7, 4, and it's going to repeat, right? 4, 6, 3, 5, 7, and so on, right? So if you look at this, basically what happens is that one time you're going to have timer 1 becoming 0 here, and it's not going to catch it here, and the next instruction cycle, which is going to be the flush of the pipeline after this branch, it's going to fetch the value here, but it's going to do the computations to figure out that it is 0 and branch, and by the time you do that it's going to be 7 cycles or whatever, right? But the thing is, so I'm going to look at TMR1, right? And the TMR1 value, maybe right at the beginning of the cycle, maybe it started at 15 because I had so many instructions right before I even start waiting in that while loop thing. All right, so I reset my TMR1 to 0 up here, and then it counts to 1, 2, 3, 4, 5, 6, and so on, right? Before it gets down to that while loop, right? But if you look at the different times that this while loop is going to run, so this is going to be 16 and 17 and go to 15999 and to 0, but that while loop is not going to catch it until it's, let's say, 3. Okay, when it's 3, then it's going to go to maybe 4 when you're resetting T1IF, and then the timer is going to go on and do 5, 6, and this is the beginning of your next iteration, in which you're checking to see if count has reached that 100 value, and maybe it reaches, even I'm exaggerating here, maybe it reaches 21 when you start your while loop, right? When you say while T1 IF at the beginning of that, maybe this is 21, and then it goes up to 15999 and then 0, and maybe while catches it when you're at 7, so this is not count 2 yet, right? And then you say T1 IF equals 0. By that time it has reached 8. When you start the next iteration in which count is 2, your timer 1 is at 9, 10, and then it's going to take a while to check if count is equal to 100 or so. So the point is, every time that you start a new iteration of the loop, there is going to be some lag, right? Your timer has already left the station, and you have already missed 0, 1, 2, 3, 4, and so on. But the point is, your loop body is about, I don't know, 20 or 30 instructions. And the important point is you want to catch these events going from 15999 to 0. So if there is some overlap, if there is, if let's say your count 0, magically your first iteration ends exactly here, right? This is impossible with this code that we have, but let's, for the sake of the argument, let's say that it's 0 here, right? So if it is 0 here, then your count 2 is going to start exactly at the timer equal to 0, going to 1, to 2, to 3, and so on. But let's say the second iteration of the loop, you're not in good luck, and basically your while loop will take quite a long time to catch that, and now your next iteration has lost all of this time, right? So if you look at individual iterations of the loop, one iteration could be 1 millisecond, one iteration could be 0.998 milliseconds, another iteration could be 1.2, well, I mean, again, I'm exaggerating, but let's say 1.2 milliseconds. But the point is, they lend time to each other. There's going to be some sort of borrowing and lending to someone else. So in aggregate, all of these overheads, your timer is going to be ahead in some iterations, it's going to be lagging behind in some other iterations, and the point is you are always going to catch these events. And who cares if you catch it a little bit early in this iteration, a little bit late in the next iteration. The point is you're going to be, on aggregate, you're going to be catching these events on time, right? So that overhead of, this overhead of 14 comes from the very last iteration. In the very last iteration that you're trying to catch that 100th 1 millisecond, you catch it late in your loop, and when you get out of here, then you have spent 14 extra cycles in addition to what you wanted to wait, right? So I don't know if this syncs right now, but looking at this picture, I hope is going to help. And you guys maybe even want to test this and single step the program. You obviously don't want to wait for 16,000 instruction cycles, but take a look at the assembly and count the number of instructions that you have, right? So this is the beginning of the loop, right? So you take a look at this, and this is 1, 2, 3, 4, 5, 6, 7, 8, and you count, and obviously you would count this as 2, and go to bit clear. Okay, now whatever number of instructions there is, let's assume that there are 17 instructions here. Okay, then set your PR1 equal to, let's say, 25, some value that is a good 5 or 6 or maybe even 10 cycles longer than the loop body that you have here. Okay, and then do a single step, and note that, for example, if you do a single step, you're going to realize that my timer 1 became 0 at this step, but then it becomes 1, it becomes 2, 3, go back to 4, 5, 6, 7, and it's going to break out of the loop and come here, right? So this would tell you that this time I had a lag of 8 to catch it. But then continue the next iteration of the count loop, and then you're going to see that 8 becomes 9, and then you branch and go up here, and then you have some of these, and you will see maybe write down the timer 1 value that you see next to each instruction on a piece of paper, and then you will see that these will bleed into each other, and you would basically be able to see that your timer 1 is catching up with the next iteration and so on. And that would convince you that the overhead that you have is not going to be accumulating. These overheads are going to cancel each other out across the iterations. But when you reset your timer 1, so let's say that you are at count equal to 2, and you enter you enter your loop with TMR 1 being, let's say, 8, right? But inside the loop, you say timer 1 equals 0. So you basically get rid of 8 and 7 and 6 and so on that you had in the previous iteration, and you restart from 0, 1, 2, 3, right? So if the while loop, if the while loop isn't very lucky and catches it when it's already done 15999 to 0, 1, 2, 3, 4, 5, 6, 7, and let's say here is the while loop catching it, and at 8 it's saying T1 if equals 0, right? All of this time that you lost plus the beginning of the next cycle that is going to check to see if count is 0 or 1, maybe this goes up to 15, all of this is lost to your loop, and in fact this is the extra number of cycles that you waited because you thought that it would be a smart idea to reset your timer and reset it, but in fact you're making things worse. And that's why you had such a really big value overall, and in aggregate those 100 cycles had a 1409. So on average you have a 14 instruction cycle overhead per loop iteration, which really works against you. All right, let's move on. I think I'm going too slow. Let's move on testing our interrupt version. So for the sake of, in the interest of time, let me comment out this part too, so that we don't have to wait for the polling of timer 1 IF next time. So let me go ahead and do this. Oh. And in fact, let me recompile so that I don't have to wait for that T1 loop. All right, skip, skip, skip. Oh, I don't want that. No. All right, so this is the time that I turn on my interrupt for timer 2. And what I want to know is, when does the interrupt routine actually flip my RB2, right? So I can just go ahead and clear my timer and do this. It's going to take a while to give me 100 milliseconds, and it gave me 16:000:14, so not bad. So my T2 is giving me 014, and that would be the same as this guy, right? So 100.0000875. So that's the overhead that I have with respect to my timer. Now, as I promised, let me show you the disassembly. The disassembly listing, all of these instructions are doing RB XORed with 1. And I don't know, what the this is unbelievable, right? I mean, look at how many instructions you have here, whereas if you have this ASM BTG port 2, just one instruction, it does the whole thing, right? So this is a good and a strong motivation for you guys to be good at assembly programming and be comfortable writing in assembly, because suppose this flipping of RB2 was inside your loop, which you had to do 1,000 times, and basically that means that instead of 1,000 times one instruction, you're going to be spending 1,000 times 10 or whatever number of instructions that you have here. And if it's critical, if it's time critical, then you'd better write this part in assembly, because the compiler wasn't smart enough to translate that with any decent number um, of instructions. Okay, so in order to test our timer 1 IF, let's go ahead and disable the interrupt here and enable timer 1's IF. So let me stop and then do another compile. And I apologize if this video became too long. I know it becomes a little bit too much when I have really long stretches of video. One thing that I do want to do is to put a breakpoint here and put a breakpoint here when that RB2 is flipped. So let's go ahead and I want to skip that. Okay, so from this point, I want to know how long it takes to do all of those, loops, quote unquote loops inside my ISR. So my interrupt routine is doing its thing. It's looping through, and you can see that my timer 1 is 22. So similar to what we had with the loop with the polling version of it, in which your overheads back to back basically compensated each other. One was taking longer, another one was taking less, but at the wait a minute, there is not going to be uncertainty here, unlike the loop, because the while loop didn't know when it could catch its timer 1 IF. But with interrupts, as soon as it happens, you would catch it. So with the interrupt, the difference is that the different times that you come into T1 interrupt, right? Maybe from the time that it happens, the TMR1 becomes 0. It would take maybe a couple of instruction cycles for the hardware to push PC and so on to get to the beginning of the loop. So maybe by the time that you say T1 IF equals 0, maybe by that time you're at 10. I'm just making up, right? And then it would take 11, 12, 13, 14 to pop the PC, pop status, and so on, and get out, right? But this time of 0, 1, 2, 3, 14 that you have counted, right? This is extra time. You were supposed to respond. In an ideal world, you would like to respond to the interrupt exactly when it happens to get to 0 from 15999 to 0 and respond to it whatever that you wanted to do in one cycle, which is impossible. But so basically in reality what you do is you have a lag of 14, you have a latency of 14 before you get out of the interrupt. But this counts towards the next iteration, right? So the next iteration, by the time you get out of T1 int and get into your main doing that while one do nothing, it will start from 15, 16 up to 15999, go back to 0, and then you have again a lag of 14 to do the next round of the T1 int, right? So even though you had a lag in responding to it, but that lag wasn't lost. That was counted. It was part of the count of TMR1, which means to get to 15999, you only need to wait for 16,000 minus that 14 things that you had, right? So all of these overheads are going to basically push things to the next time that you run T1 int, except the very last time. In the very last time that you need to respond to T1 int, then no one is going to back you with that 14 thing, so that 14 thing is going to be extra overhead for you. And you can see that in fact the overhead is 16,00021 with timer 1 interrupt. So 16,00021, which is 100.01312. So 001312. Okay, so you can see that in terms of the overheads, in each case, your interrupt has more overhead compared to polling, right? You have 21 as opposed to 14 here. You have 14 here as opposed to 9 here, right? But what is the catch? What is the advantage of the interrupt? Well, number one, you're not wasting your CPU instruction cycle. So while you're waiting for that T1 to happen, you are doing some useful stuff. So that's one thing. The other thing is here, these programs that we wrote are pretty simple. And we only have one or two devices active. And there is not a whole lot going on. And this while loop, which in assembly is going to be 5 or 6 instructions, and you go back doing it. Now, when you want to check for T1IF while you're checking this, now in the middle of this instruction, let's say T1IF has happened. Let's say T1IF became 1 at this point, right? And now you're doing the next instruction and the next instruction, and you're not aware of this because here you moved T1IF to W4. So here you're again talking about what is happening with W4. You're waiting for the next iteration to fetch the value which contains this T1IF equal 1, right? But let's say right here, when you're doing your middle of stuff, another interrupt happens with one of the devices. Maybe int 0 pin changed polarity, and you have 30 instruction cycles to do that, right? So you will not be behind by just 8 or so instructions. You would be behind by 30, 8 or 9 instructions, right? And maybe when you come back from that interrupt, another interrupt happens here, and then that adds another 30 or 40. I mean, it's unlikely that these interrupts align so that, you know, the while loop takes a very, very long time, but it's possible, right? So there is no guarantee that you would respond within, let's say, 20 cycles or so. Whereas if you're doing the interrupt with setting the priorities straight, then you can at least guarantee some things, right? I mean, you can guarantee that I'm going to respond to this thing within 30 cycles or within 60 cycles. Whereas in polling, there are no such guarantees that you can make, and anything could go wrong. Okay, I think I've covered everything that I wanted to cover. I'm going to post the code as well, but feel free to play around with it, especially with setting your TMR1 and TMR2 to smaller values and then doing single steps to see what happens and really getting it in depth that, you know, yes, you do have overhead in one loop iteration, you do have some latency, but they're going to basically do some sort of a time borrowing from iteration to iteration, and your accuracy would be actually pretty good. At the end of the day, you're going to be off by, you know, 14 cycles or 20 cycles in 1.6 million cycles, which is pretty decent. And of course, again, if you had a way of relegating that flipping of port B bit 2 to the hardware so that when the match happens between the TMR1 and PR1, the hardware would do it automatically, then your overhead would be practically zero. We don't have such a capability to, you know, make timer 2 flip RB2, but we do have such a capability with the input capture feature that you saw, but we had a whole, you know, lot of discussion on comparing different ways of capturing how many clock cycles the half period or the duty cycle of a signal was, and you could see that indeed when you relegate things to hardware, things are at their best, and you will be very accurate. All right, let me stop here.